We're going to finish up our macromolecule unit with a short little addition that is going to be about enzymes. And that's because enzymes are extremely important, and we need to focus on them a little more than just talking about them as being part of the macromolecule unit. What is an enzyme? Well, you've all heard of enzymes before probably. There are thousands of different types of enzymes, and they all have very important jobs. But most importantly for this unit that we need to understand is an enzyme is an example of a protein. So an enzyme is a protein, and it's a protein that has the job of making reactions occur. So we're going to talk about that through this unit. So let's get started. So first off, in order to use energy and hold on to energy and release energy, what we need to do is essentially it's when you break or form a bond between molecules. For example, if I want to get to the energy that is in sugars like carbohydrates, I need to break that bond. I need to break it through hydrolysis and separate those monosaccharides, that disaccharide into monosaccharides. So anytime that you break a bond, you're going to be giving off some energy. So if I want to use energy to do anything in the body or in any living organism, I need to be able to break those bonds. And that is done through a very important molecule called an enzyme. And an enzyme also are called catalysts, okay? And a catalyst or catalysis is the process of speeding something up. So what is an enzyme? An enzyme is a special protein. It's specialized to do a specific job, and its job is to speed up or start a reaction without actually being changed themselves. What the heck is that? Well, I'm going to give you all an example that you could probably relate to. I'm sure you have some friends, right? And if you have friends, you have all different types of friends. I got some friends, and some of my friends like to get in arguments. And not only do they like to get in arguments, they like to see other people get in arguments. So let's say you have two people here, right? Two individuals, and they're kind of getting into it with each other. They're yelling at each other. They have some things to say. And then some other person comes along. This person is not even involved in the fight. They're not even really involved in the fight, but they might say a couple things to speed it up. So for example, they might be like, you hear what he said to him? You hear what he said to you? And what's going to end up happening is these people are going to go after each other even more. This person is not even in the fight, but this person is making these two individuals fight more. This person is catalyzing this fight. They're speeding up the fight. They're not actually in the fight. So think of your friends, and you probably have those friends that just want to start fights all the time. They're probably the little guy in your group. That's how it was for me. My buddy Dave was always smaller than everybody else, but he had the biggest mouth, and he would go and just needle people until they would try to fight each other, and then he would get out of the way and let it happen. So that would be essentially what an enzyme does, except we're not talking about fights, we're talking about reactions. Enzymes speed up a reaction without actually getting involved in the reaction themselves. So just like these two people are getting in a fight, this person here is going to speed up that fight, but they're not actually going to be in the fight themselves. And that is an example of catalysis, or speeding up a reaction. So if I go back to the notes here, what we're just talking about. So an enzyme's job is they speed up or start a reaction. And the way they do that is with something called activation energy. Activation energy is what I'm going to be talking about for a couple minutes now. What is activation energy? It's the amount of energy required to start a reaction. Every reaction in the human body and in any living organism has the need of some energy to start it off. It's called activation energy. I'll give you an example. All right, so if I go back to this example of, let me just erase this scenario here. Let's say I built a fire, right? I took a bunch of wood and I stuck it on the floor. So I made a pile of wood on the floor, right? We got our pile of wood. Now, if I want to make this into a fire, what do I need to do to it? Well, I can do it a couple different ways, right? I can take two sticks and rub them together. That is the old-fashioned way. I could sit here, I could take two sticks and I could rub them together, and if I rub them together fast enough, it'll create some heat energy, and that can start the fire, right? And I can get the fire started, and I would get my flame. That fire is not going to start by itself. If I just pile up this wood on the floor and let it sit there, it's going to sit there forever and it will never get started. So I can rub two sticks together and I can get that fire going. I don't know if you've ever tried to do that before, but it takes forever. I've never done it before, and it's really hard to do. What's our other option we could do? Well, I could take some gasoline. I can take some gasoline and I can pour some gasoline on that fire. And now that thing is going to be like, right? It's going to take off. It's going to get really hot really fast. Which of those two is the better option? Well, if I take a look at both of them, they both produce the same amount of fire, right? Once that fire gets started, that fire is going to burn, whether I start it with sticks or I start it with gasoline. What's the difference here? This is going to happen way faster. So both of these examples are going to start a fire. The difference is this one would be with the help of an enzyme. What the enzyme does is it makes that fire start quicker. Where if I'm just using two sticks rubbing together, it's going to take forever and that fire's never going to take off. So activation energy is very simply the energy required to start a chemical reaction. Now, one thing you have to remember though is what enzymes do is they decrease the amount of energy needed to start that reaction. So if I take two sticks and rub them together, eventually I will get a fire, but it could take me hours to make that happen. Or I could just throw a little gasoline on there, hit it with a match, and boom, I got my fire. Which is the better option? I'm going to go ahead and say gasoline in that scenario because it's going to have that fire going. So this diagram is a good job of showing you that. So one example of an enzyme would be lactose, and we're going to talk more about that later. Lactose is an enzyme, or is a sugar, right? Lactose is in milk. Lactose is made up of glucose and galactose together. Without an enzyme, it's going to take a whole lot of energy to break that lactose down into glucose and galactose. Now, let's say I add an enzyme, and that enzyme is called lactase. So you may have heard of people that are lactose intolerant. I'm lactose intolerant. People that are lactose intolerant, they can't break down sugar very easily because they're missing this enzyme. So it takes them a very long time to break that sugar down, and they can't break it all down. If you look at my diagram down here, though, this is with an enzyme called lactase. That lactase allows that sugar to get broken down much faster. So what are we looking at here? Well, this top diagram, this person has to push way harder to get that ball up to the top, and then it comes down the hill. So this would be without an enzyme. This would be with an enzyme. So if you take a look at these two diagrams here, they both have the same amount of energy being released. The amount of energy being released is the same up here as it is down here. The difference is how much energy had to go in to make it happen. This required a whole lot more energy going in than this did. So which is going to happen faster? The enzyme one's going to happen faster. And you're going to get the energy that you need very quickly. So the difference between with an enzyme and without an enzyme is how much activation energy you need to get that process going. And all you're doing is cutting that down. This is another good diagram that shows you that. So if you take a look here, right, we have, this is the amount of energy that needs to get used, and this is the rate of reaction going this way. So if I take a look here, both of these scenarios are going to be how much energy goes in. So if you take a look at this red line, this is without an enzyme. It takes way more energy to get this process going than with an enzyme. This is with an enzyme, it takes way less energy. But once the energy's in, this is how much energy actually gets given off. So if we're talking about making a fire, this is how much energy gets given off by the fire. It doesn't matter once that fire gets started, the same amount of energy gets given off for with an enzyme or without an enzyme. The difference is how much energy had to go in. So if I have an option of which one I want to use with the enzyme because the difference here is pretty drastic. It's going to take way more energy to get this process going. So when you're thinking about enzymes, enzymes are going to decrease the amount of activation energy needed to make the reaction happen. But the amount of energy that gets given off is still going to be the same. We're going to finish up here with just two more terms, and then that's it for the period. We have exergonic and endergonic reactions. And exer should hopefully make you think of exit, okay? Think exer, exit, ender, enter, okay? Exergonic reactions give off energy. They don't use energy, they give it off. You need activation energy. Every process needs activation energy. So once we get past that activation energy, it just gives off energy as a byproduct. An example of that would be a fire, right? Once you put that flame on there, that fire is going to burn. It's going to give off heat energy. That's a great example of an exergonic reaction. An endergonic reaction uses energy. So what would that be like? That would be like melting ice. If I want to melt ice, I need to keep adding heat to it until that ice melts into a liquid. So this diagram here just shows you those two things. So what you're showing here is an exergonic reaction. The energy is being given off. So the amount of energy being given off is going to keep going up. So you're going to have a whole bunch of energy being given off by the product. That is going to be an exergonic reaction because the energy is being given off. You start with a certain amount and you end with less. That gets given off by the system. So like burning a fire would be an exergonic reaction. An endergonic reaction would be like pushing a ball up a hill. You got to keep pushing it. You got to keep adding energy the whole time. Eventually you get the ball up that hill, but it uses energy the whole time. Exergonic is like a ball rolling down the hill. Once you get it up to the top of the hill, it just goes. You don't need to add any more energy to it. So this would be like melting ice. If I want to melt ice, I have to keep adding heat to it to get it to melt. And that's it. So just make sure you understand that an enzyme speeds up a reaction, but it doesn't actually change itself. So the enzyme just makes the reaction happen faster, but it doesn't become part of the reaction. It does that by decreasing activation energy. It's less energy that needs to go in to make that process happen. And then just make sure you know the difference between an exergonic and an endergonic reaction. Exergonic reactions give off energy. Endergonic reactions use up energy. Thank you very much.